Energy efficient routing. In most sensor network channels, these devices acquire data from the environment and send it to other nodes for further processing and analysis. When such destinations are not within the radio range of the source node, intermediate sensor nodes are used as relays. Routing protocols for wireless sensor networks are used to transmit messages from source to destination. They can be classified as unicast, broadcast, multicast. What is unicast routing? Unicast routing is used to send a message generated by a sensor node to a single destination or sink. Broadcasting is used to send a message from a sensor node to every other node in the network. Multicasting is used to deliver messages from a single source to a set of destinations. Multicasting protocols try to minimize the consumptions of network resources. For instance, sending one copy of the data to each destination using unicast is not considered as multicast routing. Energy efficient unicast. Energy efficient unicast routing appears to be a simple problem. Take the network graph, assigned to each link a cost value that reflects the energy consumption across the link, and pick any algorithm that computes least cost path in a graph. The Digista's shortest path algorithm is used to obtain routes with minimal total transmission power. In fact, there are various aspects how energy or power efficiency can be consumed of in a routing context. Philoppiger shows an example scenarios for a communication between nodes A and H, including link, energy cost, available battery capacity per node, minimize energy per packet. The most straightforward formulation is to look at the total energy required to transport a packet over a multi-hop path from source to destination. The goal is then to minimize for each packet this total amount of energy by selecting a good route. Minimizing the hop count will typically not achieve this goal, as routes with a few hops might include hops with large transmission power to cover large distances. But we are aware of distance independent constant offsets in the energy consumption model. Nonetheless, this cost metric can be easily included in standard routing algorithms. It can lead to widely differing energy consumption on different nodes. Figure 320, various example routes for communication between nodes A and H, showing energy cost per packet for each link and available battery capacity for each node. In the example figure 320, the minimum energy route is ABEH, requiring 3 units of energy. The minimum hop count route would be ADH, requiring 6 units of energy. Maximize the energy lifetime. Energy efficient transmission is at best a means to an end, and the actual end should be the optimization goal. The network should be able to fulfill its duty for as long as possible. Network lifetime, which is defined as the time until the first sensor energy runs out, is an important performance metric is wireless sensor networks. Routing considering available battery energy. Maximizing the network lifetime is clearly a useful goal, as the finite energy supply in nodes batteries is the limiting factor to network lifetime. It stands to reason to use information about battery status in routing decisions. Some of the possibilities are maximum total available battery capacity. Choose the route where the sum of the available battery capacity is maximized without taking needless detours. Taking one of the intermediate nodes in figure 320, route ABEGH has a total available capacity of 6 units, but there is only because of the extra node G that is not really needed. Such detours can, of course, arbitrarily increase this metric. Hence, ABEGH should be discarded as it contains ABEH as proper subset. Minimum battery cost routing (MBCR). Instead of looking directly at the sum of available battery capacities, along a given path. MPCR instead looks at the reluctance of a node to route traffic. This reluctance increases as its battery is drained. For example, reluctance of routing cost can be measured as the reciprocal of the battery capacity. Then the cost of the path is the sum of these reciprocals, and the rule is to pick that path with the smallest cost. Since the reciprocal function assigns high cost to nodes with low battery capacity, this will automatically shift traffic away from routes with nodes about to run out of energy. In the example figure 320, route ACFH is assigned a cost of 1 divided by 1 plus 1 divided by 4 is equal to 1.25. But route ADH only has cost 1 by 3. Consequently, this route is chosen, protecting node C from needless effect. Minimum max battery cost routing (MPPCR). The scheme follows a similar intention here protect nodes with low energy battery resources. Instead of using the sum of reciprocal battery levels, simply the largest reciprocal level of all nodes along a path is used as the cost for this path. Then again the path with the smallest cost is used. In the sense, the optimal path is chosen by minimizing over a maximum. The same effect is achieved by using the smallest battery level along a path and maximizing over these path values. This is then a maximum minimum formulation of the problem. In the example of figure 320, route ADH will be conditional max minimum battery capacity routing CMM-PCR. This scheme works conditionalized upon the actual battery power levels available. If there are routes along which all nodes have a battery level exceeding a given threshold, then select a route that requires the lowest energy per bit. If there is no such route, then pick that route which maximizes the minimum battery level. Minimize variance in power levels. To ensure a long network lifetime, the strategy is to use up all the batteries uniformly to avoid some nodes prematurely, prematurely running out of the energy and disturbing the network. Hence, routes should be chosen such that the variance in battery levels is different.